Without any further ado, I'd like to pass on to Ryan, our applications engineer, who will be performing a live demo of our Typhoon HIL technology in action. Ryan?
All right. Thank you very much, Guido. That was pretty informative. My name is Ryan Deal. I'm an applications engineer here at Typhoon HIL. And I'm going to be walking through a demonstration with you guys, showing off a simple microgrid, and we'll test some real controllers here. So in this application, we're going to have two controllers that are going to be under test. The first controller is TI-2808, and that's going to be our energy storage controller. The second controller is a TI-F28377D, which is going to be our solar inverter controller. So all of the other simulation in this demonstration is going to be simulated within the HIL. So the generator, the grid, the loads, etc. So you'll see this is actually what I have in front of me right now. Just running my laptop with a single hardware in the loop unit 602, and we have a breakout board to talk to these two controllers. So there's two controller cards, both TI-TSP controllers. Okay, so let me go ahead and move on to the actual control center platform. Great. So this is Typhoon HIL Control Center. We wanted to make this the single place you go to do all of your modeling, your real-time simulation, the compilers built in, the scripting, the script creation, and the running of those scripts. So I'm going to do all of this in real time just so you get a really good feel for the tool and the responsiveness, and let's dive into this schematic. Great. Okay, so let's go ahead and dive into this schematic. So like I said before, our component library is on the left here. Very simple drag and drop. So you just pull in and you wire up. We wanted to make this as easy as possible and make this as efficient as possible to build your models and really make the building of the model a quick process to where you can spend most of your time in real-time simulation and actually spend most of your time tuning and testing. So on the right-hand side here, you'll see we have a strong balanced grid that we're simulating with transmission lines, and we also added some switches to be able to simulate some faults in our grid. So phase-to-phase and line-to-ground within the grid. These transmission lines are pretty important as well because they really create that distributed energy simulation that we need. So here we have the switch for the grid to the islanded mode, which would connect to our genset. And this is an average generator model. There is a couple more generator models within the component library that you'll have access to. And on the microgrid side, you'll see that we have in this subcomponent block, there is some simple meters for voltage measurement, current measurement, RMS, as well as some DSP functionality here in the blue. So over here we are simulating our battery energy storage system. So here we have the capability to do some different chemistries. For this application we're using lithium ion. You can go in and actually look at these battery curves, which are lookup tables. And you can define these curves very easily within the Typhoon toolchain. You're actually able to go in and do this through the waveform generator. And you can use this to basically define your waveforms for batteries, for PVs, etc. So jumping into this battery storage inverter, you can see here we have 3-phase 2-level IGBT converter and a filter over here as well as a contactor. So to get a good idea of what's going on inside this on the modeling, from a modeling standpoint. I'm going to jump into the documentation hub, which is actually one of my favorite features about the Typhoon HIL Control Center. There's a ton of information built into this library, and even as an application engineer, I use this very frequently to find all the information I need. So we're going to jump into the schematic editor library document. And I'm going to cheat a little bit because I know which page it's on. Great. So this is the component that we're modeling, and you can see the switch topology is here. So let's back out to the PV and get some focus on that. You'll see we have the panel here with its capacitance. And if we jump into the inverter, we have some meters, a filter, and a T-type inverter. So let's pull that inverter up to give you guys a feeling for it. So this is the solar inverter model. Okay. So also in this microgrid, we have a constant power load, which is defined just like or with a lookup table as well. And we have an induction machine, and it also has some DSP modeling built into this. Okay, great. So I'm going to go ahead and start compiling this and give you guys a feel for how the compilation process looks. We are compiling to an FPGA on the HIL, but this is not going to take hours or days. We're compiling softcore that's pushed to the unit, so it's in a matter of minutes. So that really gives you the capability to go in and tune your model properly and not have to worry about crazy long compilation times. So while this is compiling, I'd actually like to go in and start talking about how this maps to hardware. So this is all simulation, obviously, and if we jump into here, we can see that we have some meters here, and those meters and these gate drives are basically mapped to the actual hardware. So you'll notice this is a digital input on the hardware in the loop unit. So the controllers will be sending PWM signals at very fast speeds to our hardware in the loop unit, which we will then measure and simulate the power, which is then measured here from the simulation, and these will then output to, or from analog outputs back to the controller, providing us with the full closed loop system. So it's good to, I guess, while this is finishing up, we'll go ahead and jump into the control center. So the HIL control panel is basically where you're going to be doing all of your real-time simulation. So the model is loading up to the hardware in the loop unit. And you'll see here on the left, we have the space holder for defining all of your sources. And on the right, we have all of our mapping to hardware. So those current meters we were looking at earlier, we'll actually take these and map them here instead of scaling at an offset if it's needed, and that will map it to that actual channel. So I'm going to load up a predefined settings file so you guys don't have to watch me click on a whole bunch of things. And you'll see here that show an actual mapping to some hardware for you. So we have the solar inverter subsystem with IA, B, C, and you can see here solar inverter.IB, solar inverter.IA, solar inverter.IC. So those are mapped to the actual hardware channels that we're outputting to the controller to simulate that power. So this microgrid is running at 220 volts, 50 hertz. These controller firmwares were developed for a European grid. So in the case that your controller was for the US grid, you could simply go in and change this frequency to 60 hertz. But for the case of this demo and these controllers, we are going to stay at 50 hertz. So the PV settings can also be defined here, also a lookup table. So you can view this PV curve and how it's going to behave. So let's go ahead and start the simulation up. So here we see that we have voltages and currents from that PCC measure subsystem. And you can see here that the solar inverter, while it's disconnected, is trying to inject some current into the system to boot up. And it actually caused this PTV flag. That is actually a good thing. That means that the controller is not support, does not support being disconnected right now. So there is something in the firmware that needs to be fixed and changed. So what I'm going to do is I pop this window out. I'm actually going to minimize it and show you guys the power of the custom user interface. So let's go ahead and clear this flag. And let's load our custom UI panel. And this is the view where you can start working to develop your macros, and you can test in real time and really get a feel for the simulation while you're running it. So let's see here. Great. So you can see here we have our grid voltages and currents. We're outputting a little bit of power. Let's actually reduce this load power a little bit. And I want to go ahead and jump to the genset. So we're going to switch to islanding mode here, and we'll see how the generator responds to that. So you'll notice we have the genset's outputting 5 kW of power, and it's trying to correct that frequency back to 50 hertz. So it's slowly moving back up. And the solar inverter is still going to town trying to inject current and turn on, but it's not able to boot up yet because the contactor is off, so it's disconnected from our microgrid. And I can show you this in the schematic. So this contactor is disabled. We currently have the genset hooked up and battery storage disabled. And let's go ahead and turn on this induction machine. So you can see the induction machine is pulling in about 2 kW of power on top of our load power here. So let's go ahead and power up the ES, or the energy storage controller. So you can see here we just booted on the energy storage controller, and it has a 0 current at the beginning. But if I go and I send the command to it to set the reference, I can actually change it to maybe, like, let's say 1 kilowatt. There we go. So you can see that the energy storage controller is now booted on, and it's providing that current to our microgrid. And you can see over here we have our voltage, and the charge is very slowly diminishing on that battery. So let's go ahead and switch back to the grid, and I want to show you what we can do with this solar inverter controller. So back to the grid, we can see once again that we have that change in frequency. So the grid is working to stabilize back to 50 hertz, or that's the generator, sorry about that. but it's also working to stabilize itself. At this point, I'm going to go ahead and turn on the solar inverter controller. So I'm going to go ahead and switch that contactor on, and the controller will take a little bit of time to boot up. I can change the irradiance a little bit. There we go. This specific controller has a parameter to where it actually cannot go over 1,000 volts, otherwise it'll automatically disconnect. So if I actually wanted to play with this irradiance, I could give it too much power and it'll automatically disconnect. So we can see here we have a very easy ability to measure our current versus our voltage and the power, and it's useful for maximum power point tracking, etc. Let me change this reference a little bit here. So while this is hooked up, I actually want to start running some macros. So in the custom UI panel, you're actually able to go in and define these macro buttons through some simple Python code. And the point of this is to develop these macros in real time while you're running your simulation to really start building some solid testing scripts that you can then automate and fully test the robustness of your controller and make sure that your firmware is actually solid. So let's go ahead and check out this frequency sweep macro code. So here you can see we have all Python. We actually have this API wizard to kind of give you the easy capabilities to go in and easily add code. So you can see here we're just looping through some different frequencies and changing those sources. But say I wanted to add a contactor switch or a fault in here as well. I would go ahead and say, yeah, let's add this grid fault. And I can insert it right here. You can see that it imports perfectly into the code. And this gives you the capability to easily add some more functionality and build out your test scripts. There's also further documentation on these API commands within this documentation hub. So let me run a frequency sweep, and let's see how the solar inverter responds. So you'll see the change of frequency in the grid, and the controller seems to still be hanging on, so that's good. Let's inject some harmonics. And set back to nominal. And let's do a low voltage right-through macro as well. Great. So we can see here that the controller actually disconnected. So it did not, I guess, stay functional through that test. So that's good. That means we need to develop our code and make it more robust. And you can see the controller is actually trying to reconnect right now, and it has successfully started back up. So we want you to start developing these macros, build up these tests, and really start automating these testing processes so you can really test your controller firmware and get a really solid feel for what your controller is going to do when you hook it up to real hardware. So you can do this code editing through that API wizard like I was showing. You can do it through the script editor, which is a Python IDE that we provide, or you can use pretty much any other Python IDE to develop these test scripts. And we also offer a pre-certification suite of scripts that are verified by national labs to support standards such as BDEW, IEC 61850, and UL 1741 with California Rule 21. So in conclusion, we have this microgrid running in real time at a 1 microsecond step time with two real controller or converter controllers. And it's, as you can see, it's pretty easy to build up a schematic and run these tests. We really want you to be confident in your controller firmware and optimize and test before you ever hook up to real power. And at this point, I'll hand things off to Guido again, and we look forward to answering some questions.